Hello and welcome to our lesson on exponential growth and decay and compound interest. This is going to be from section 9.7 in our text. Let's get started. Now the first thing you're probably going to notice is the big yellow X over the compound interest formula. That's because this particular formula was covered in section 9.3, and although it would be okay to cover this in this section, since we've already covered it, I'm not going to spend time doing examples related to the compound interest formula. What I would like to point out, though, is that this formula is pretty much the same as the compound continuously and the exponential growth and decay formula. So let's say that we're going to let u equal 1 plus r over n. So what we can do by doing a substitution into the compound interest formula, we can replace all of the stuff in the parentheses with just u. And that'll give us the formula a equals p u to the nt. Okay? Now notice that this formula is exactly the same as the compound continuously and the exponential growth and decay in its layout. So you've got the A, which is the amount of stuff or the amount in the account, the P, which is the principal, the U, which will be a constant given the rate and the number of compound periods. All of that will simplify to a number, so that'll be just a constant, and then raised to the n times t. Alright, so at this point, let's shift our focus to the formulas at hand, and I want to show you how easy it is to solve for any of the variables in the formula, given that e is not going to be a variable. Remember, e is a number like pi. The value of e is about 2.72. approximately. And also remember that it's not going to matter whether I use the a equals p e to the rt or the exponential growth or decay formula to work with. They're both the same format. Alright, so working with a equals p e to the rt, let's assume that you want to solve for a. That would be the easiest scenario, where you would have to be given the P, which is the principal in this case, the rate, and the time. The next easiest would be, what if we want to solve for P? Well, since P is multiplied by e to the RT, you would simply divide both sides by e to the RT, and that would isolate P. And in this case, you would have to be given A, R, and T in order to solve for P. Now, if you're solving for either the rate or the time, both of those are going to require the same steps. So let's walk through the steps to isolate the exponent, and then you can either pick R or T to solve for. The first step would be to isolate the exponential piece, which means that you would need to divide both sides by P, and that would give us A over P equals e to the RT. And the next step, in order to get the R or the T out of the exponent position, you're going to want to take the natural log of each side. Now, why that's necessary is because once you have the equation in terms of logs, you can access the properties of logarithms. And one of the properties we talked about was the power rule, which says that you can bring the exponent down to the front of the log. So this would give us natural log of a over p equals RT, remember that's multiplication, R times T, times the natural log of E. And then the cool thing about natural log of E, that's 1. Remember, ln means log base E, and if the bases match, they cancel, and the exponent is the answer. So anytime you're taking the natural log of e, that's going to become 1. And in this case, 1 times anything is itself, so we don't really need the times 1. We just have RT at this point. And now you can either solve for R or T, depending on which one you need, by dividing both sides by the other. So if you're trying to solve for T, you would divide both sides by R. Or if you're trying to solve for R, you can divide both sides by T. Either one. And that's basically the process for solving for any of the variables that you might need to isolate in either one of these formulas. And now we're going to move on and look at some specific examples. All right, first example, problem number 7 from the text. It says, suppose that $10,000 is invested at an interest rate of 5.4% compounded continuously. Now this is important because this tells us which formula we're going to be using. So compound continuously means we're using the formula A equals P e to the RT. It says the 10,000 is invested, so the 10,000 is the principal, the 5.4% is the rate, and part A says find the exponential function that describes the amount in the account after time t. So then there's going to be two variables. We're going to replace P and R with what they're equal to. Okay, so for part A, using our compound continuously formula, oh, and it does say the word function. So this is going to be A of t equals the principal, which is 10,000, e to the r, 0.054. Remember, you have to move that decimal 2 places to work with the percent. And then t is because it says after time t. So t is going to be our input. A of t is our output. That is our function. Now for part B. It wants to know what is the balance after 1 year, 5 years, and 10 years. And that means we're just going to substitute for t the values of 1, 5, and 10. And that's going to give us the amount in the account. So first we're going to have A of 1 equals, and the easiest way to do that is with our calculator. Alright, so pulling up our Casio Class Whiz, we're going to type in 10,000, e to the, to get the e to the, that's going to be Shift LN, to the 0.054, and here we can just click times 1, and that'll give us A of 1. The amount after 1 year is $10,554.85. Remember, you do want to round to the nearest penny when you're working with money, unless specified otherwise. Now then, to make the other two values super easy, we're going to use our calculator secret weapon, which is the backspace button. And we're simply going to delete the 1 and insert a 5. And this will give us the amount in the account after 5 years, $13,099.64. Alright, so there's the answer for 5 years. And then again for 10 years, we're just going to backspace, delete the 5, input a 10, and round to the nearest penny. And the answer for 10 years, $17,160.07. And for part C, it asks for the doubling time. Doubling time means how long will it take for our money, our investment to double. And I think what I'm going to do is show you how they come up with the formula for that. So using our compound continuously formula, knowing that P represents the principal, if you want the doubling time, then the amount would have to be twice as much as P. So we can say that the amount we're looking for is twice P. 2P equals P e to the RT. And then if we solve for T, we can get the formula for the doubling time. So to do this, we're going to divide both sides by p, which will get the p's to cancel completely, e to the rt, and then at this point we want to take the natural log of both sides. And just so you know that there is a shortcut here, ln and e cancel and brings down the rt. That's kind of sidestepping the power rule, knowing that the exponent is going to become a coefficient, so this rt is no longer a coefficient, equals natural log of 2. And remember, we want the doubling time, so we want to solve for t, which means we need to divide both sides by r. And now you have the formula for the doubling time. Natural log of 2 divided by r. So how long will it take this to double? Well, the doubling time is going to be the natural log of 2 divided by our rate, which is 0.054. And again, bringing up the calculator for that, as a fraction, natural log of 2, don't forget to close your parentheses, divided by 0.054. So we're going to go ahead and round that to the nearest whole number, even though they don't specify where to round to. That would be 13 years. And do you understand what that means? That means it's going to take 13 years for our $10,000 investment to grow to $20,000. And just for fun, if you want the triple time, all you have to do is replace this 2 with a 3. Next example, number 9. In 1970, Amos Flora of Flora, Indiana, discovered teeth and jaw bones while dredging a creek. Scientists determined that the bones were from a mastodon and had lost 77.2%. They lost that percent of their carbon-14. They want us to know how old were the bones at the time they were discovered. So this is an example of an exponential growth or decay model. Here, the carbon-14, once an animal or a plant or something dies, it starts to lose carbon-14. So this is going to be exponential decay. Our formula for that is A equals A naught e to the kt. And what we're going to have to know in order to work this problem is the half-life of carbon-14. That's one of those facts that you're going to have to know in order to figure this out. So I've looked that up and found that the half-life of carbon-14 is 5,730 years. Now the reason we need that is because we need to find the decay constant. And that value is based on the material or substance or whatever you're dealing with. So here we go, finding the decay constant based on the half-life of carbon-14. We do not know the initial amount of carbon-14 in this mastodon. We don't know what the initial amount was, and that's okay. Because we know the half-life of carbon-14, we can say that after that amount of time, 5,730 years, we will have half of the original amount of carbon-14. So we can set up this formula like this, knowing that half of the original amount will be left after 5,730 years, and then we should be able to solve for our decay constant. So we're going to divide both sides by A naught. Notice that gets both of those to cancel. And then we have 1/2 equals e to the 5,730k. That's multiplied, so it doesn't matter what order they're in. And then I'm going to take the natural log of both sides. Remember, ln and e cancel, and the exponent comes down. So then that'll give us the natural log of 1/2 equals 5,730k. And then if we divide both sides by 5,730, we're going to have our decay constant. We're going to be doing as a fraction natural log of 1/2 I'm going to use 0.5. 0.5 is the same as a half. Divided by 5,730. Oh, and notice that it gives it in scientific notation. Now this times 10 to the negative 4 means that I need to take the decimal and move it 4 places to the left to get the actual value. So that's going to be negative 0.00012, rounded to the nearest hundred thousandths. Sometimes it'll specify how far to round that. If you wanted to go one more place, that 9 would round the 0 to a 1. So if you want to go 6 decimal places to make it a little more accurate, that is the rate of decay, or the decay constant. Now we can set up our formula and solve for the actual question, which is how old were the bones? The initial amount of carbon-14 we still don't know. E to the negative 0.000121, that's from our decay rate. And since we're looking for how old were the bones, that means we're looking for time. On the other side is where this percent comes into play. And then this is where I need to make sure that you understand the formula. This value here, A, is the amount of stuff left after a certain amount of time. It is the amount remaining. So if it lost 77.2%, what percent was remaining? Well, to figure that out, you would do 100% minus 77.2% would give you the percent remaining, which is 22.8% of the carbon-14 was remaining. And so we can plug that in over here. We can say 0.228 of the initial amount was remaining. Does that make sense? That if you multiply the initial amount by 0.228, you will get the amount of carbon-14 that was remaining. And so at this point we would divide both sides by A0, which is going to give us 0.228 equals E to the negative 0.000121t, and then we can take the natural log of both sides. Natural log and E cancel each other out, and that'll give us the natural log of 0.228 equals negative 0.000121t. Dividing both sides by the coefficient of t is going to give us a value of t, which is whatever this is from the calculator. So as a fraction, natural log of 0.228 divided by negative 0.123121, 12,218 years. So the answer to the final question, how old were the bones at the time they were discovered? They were 12,218 years old. All right, next example, number 13. The data in the following table show that the percentage of adults in the United States who are currently married is declining. Assuming that the percentage of adults who are married will continue to decrease according to the exponential decay model, we want to use the data from 1960 to 2012 to find the value of K. And then it wants us to write an exponential function that describes the percent of adults married after time t in years, where t is the number of years after 1960, and that's also important. So we're going to be using the data from 1960, which is 72.2%, and 2012, which is 50.5%, to find our decay rate. How does that work? Well, given our exponential growth and decay formula, we know that A naught would be the initial, in this case, percentage of married adults. And the initial amount would be the amount in 1960, which is 72.2%. The amount later on down the road would be the amount of people married in 2012. And that percentage is 50.5. So you can see from the initial amount to the final amount, that number is decreasing. And hint, hint, that means that our decay rate, our value for k, should be negative, because a negative exponent indicates decay, not growth. Then we're going to have e to the k, remember k is what we're looking for, times t. Now this t is the amount of time that it takes to get from the initial amount to the final amount, which means we need to take our final time and subtract our initial time to give us how many years it took to get there. With the calculator, 2012 minus 1960, 52 years. And so that's what we're going to plug in for t, and then we're going to solve for k. Alright, so dividing both sides by 72.2 to get rid of our coefficient of e, and we're going to need to calculate this out to a decimal or a reduced fraction. As a fraction, we got 50.5 over 72.2 as a fraction. Okay, now that we don't have a coefficient of e, we can stick an ln in front of that e. Remember, whatever you do to one side, you have to do to the other. So we're taking the natural log of both sides, because ln and e cancel, and the exponent comes down and becomes just 52k. Okay, that's multiplication, so I can switch the order. This is natural log of 505 over 722. And then to finish it off, to solve for k, we're going to divide both sides by 52. And again, that should be no trouble with our calculator. We're going to have the natural log of a fraction, 505 over 722. Don't forget to move over and then down. Notice when you're inputting this in the calculator, you need to make sure it looks exactly like it does on your paper in order to get the correct answer. Oops, and that's in scientific notation again. So times 10 to the negative 3 means I need to move that decimal 3 places to the left to get the actual value. That's going to be 0.00687. Negative 0.00687, rounded to 5 decimal places. If you wanted to go one more decimal place, you could. I think I will, just to be consistent with what I did in the previous example. We're going to go to 6 decimal places. Of course, you would want to round to whatever decimal place the instructions specify, if it specifies. So this is the first part of part A, where they want us to find the value of k. Now we're going to write the exponential function that describes this decay. So remember, we need to use function notation for that. So a of t will equal, the initial amount is going to be 72.2, because that is the percentage that we started with. We're starting in 1960. E to the negative 0.00687 t. And that is our exponential function for this particular scenario. And that's going to do it for part A. Now for part B, they want us to estimate the percent of adults who are married in 2015 and 2018. So what that means, it means we're going to need to figure out how long will it take to get to 2015 and 2018 from the initial date of 1960. So the first thing we're going to have to do is take 2015 minus 1960, and then 2018 minus 1960, and that'll give us the 2 times that we're concerned with. And 15, 16, 17, 18, this is going to be 3 years later, so 5, 6, 7, 8, I'm guessing that's going to be 58 years. And so now we can figure out the amount of people married after 55 years, and that will correspond to the year of 2015. And this is just a plug-and-play problem. 72.2 e to the negative 0.006874 times 55. Replacing t with 55, and then whatever this calculates to be is going to be the percent of people married in 2015. And again, we're going to use our handy-dandy calculator for that. 72.2 shift ln e to the negative 0.006874 times. I'm going to go ahead and put times. If you want to put parentheses, you can, but it's easier to just say times 55. And rounded to the nearest tenth. We're going to round to the nearest tenth because the percents in the table are rounded to the nearest tenth. That's going to be 49.5%. Now, what's going to make me feel better about that answer is if it is less than the percent in 2012. Remember, this is a rate of decline. The percentage of married adults is on the decline. So in 2015, there's going to be even less than 50.5% married, which there is according to this calculation. And we're also going to calculate A of 58, just like we did before, replacing T with 58, and whatever that works out to be will be the percent of adults married in 2018. Now the fastest way to do that with our Casio is to just back up, delete 55, and make it a 58. And that's 48.5%, which is even fewer than in 2015. So there's the answers for part B. This is the percent in 2015. This is the percent in 2018. And then for part C, at this decay rate, in which year? That means we're looking for time. Will the percent of adults who are married be 40%? That's going to be the A that we're looking for. So to answer this question for part C, we're going to get down to 40%. That's going to be our value for A in this formula right here. A is 40%. The A naught is still going to be our 72.2 forever in this example. E to the negative 0.006874, and T is the variable. So T is going to remain T, and then we're going to need to solve for T. Alright, so the first step to solve for T would be to divide both sides by the coefficient of E, 72.2. Get those to cancel, and then we're going to need to calculate this value out with a calculator. So that's going to be 40 divided by 72.2. And you can leave that as a fraction. That would give you the most exact, most precise value for T. And so I'm going to leave that as 200 over 361. And now we just have e to the exponent. And at this point, we can take the natural log of both sides. Natural log and e cancel, and the exponent comes down to the front using the properties of log, so that's no longer an exponent. And once we get to this step, we're one step away from the answer. We simply need to divide both sides by the coefficient of t. That's going to get those to cancel, which is going to isolate our t. And then we simply need to put all of this in the calculator to find out how long it's going to take for the percent of married adults to reach 40%. All right, so here we go again with a fraction to start off with. We've got the natural log of a fraction, 200 divided by 361. Move over, close, move down, and then for our long decimal number, negative 0.006874, and we're going to round that to the nearest whole number, which would be 86 years. Now listen, it's going to take 86 years to get down to 40%. Okay, but now remember, what they really asked, they said in which year. They didn't say how many years, they said in which year. And that means that you're going to have to remember what year to count from. So our starting date was 1960. Remember, it says where t is the number of years after 1960. So to figure out the when, we're going to have to take 1960 and add 86 to get the date that will happen. And that's going to be in the year 2046. And I'm going to double box that because that's really the answer they asked for. It'll take 86 years, but from 1960, that's 2046. And for our final example in this lesson, number 17, it says, in a town whose population is 3,500 people, a disease creates an epidemic. The number of people in infected T days, that's important, T is in days this time, after the disease has begun, is given by this function. It says, for part A, how many are initially infected? Now, initially always means at time 0. So to figure out that value, we're going to have to calculate n of 0. And you're thinking, no, I'm not. I'm saying, yes, we are. N of 0, that's going to be 3,500 divided by 1 plus 19.9 e to the 0. Because if I replace t with 0, 0 times anything is 0, and that'll make that exponent 0. Now, do you remember what anything to the 0 power is? That's right. E to the 0, anything to the 0 is 1. And so that's going to simplify down to just 19.9, because that was multiplied by 1. 1 times anything is itself. And then that's going to simplify to 3,500 divided by 20.9. And we're still going to need a calculator for that. 3,500 divided by 20.9 as a decimal is 167 point. Now listen, you can't have half of a person. Remember, n is the number of people, so we're always going to need to round this to the nearest whole number. Does that make sense? You can't have part of a person. So 167 people. That is the initial amount of infected people. 167 were infected initially. Part B, find the number of infected after 2 days, 5 days, 8, 12, 16, 1, 2, 3, 4. That's 5 values that we're going to have to calculate. So for part B, we're going to be calculating n of 2, n of 5, n of 8, n of 12, and n of 16. Now with our handy dandy Casio, this is going to be super easy barely an inconvenience. Let me show you how easy this is. First, we're going to start with a fraction. We've got 3,500 over, and then we're going to input the rest of this function here. 1 plus 19.9 e to the, which is shift ln, e to the negative 0.6 times t. So for the first value, it's going to be times 2 equals, and we need to round that to the nearest whole number, which is 500. So how many people were infected after 2 days? 500 people were. Now, for the rest of these calculations, again, I said this is super easy with our Casio. We just need to backspace until your cursor is next to the 2. You're going to delete the 2 and insert the next value, which is 5, and then round to the nearest whole number, 1,758. And then you just rinse and repeat. Backspace to the 5, delete, next we have 8, 3,007. Can you see the number of infected people is increasing, as it should? Next, delete the 8, next we have 12, 3,449. And last but not least, delete and 15, 3,491 people infected. Now, can you see that the rate of infection has slowed down? I mean, it jumped from 167 to 500 in 2 days, right? That's a big jump. And then from 500 to 1,758, again, that's a pretty big jump in just 3 more days. But then from 12 days to 16, that's a 4-day increase. We only had about 50 or so people more infected. Now, the reason the rate of infection is slowing is because the population is only 3,500. So right here, after 16 days, almost the entire population is infected. Okay, so let's look at part C. Using this model, can you say whether all 3,500 people will ever be infected? And it wants us to explain that. Well, what I would like to point out is that this is an exponential function, and we know that every exponential function has a horizontal asymptote. Now, what does that mean? That means that there's going to be a value that the graph is approaching but never touching. So for part C, we're going to say no, because if you look at the pattern, as the number of days increase, the number of infected is approaching 3,500. It's approaching the total population, but no matter how many days you increase it, I don't care how many days you increase it, it's just going to continue to approach this number, but it'll never get there, because the function is exponential, which has a horizontal asymptote. So when it says explain, we're going to say no, because the graph will approach 3,500 but never get to 3,500. And I think to drive that point home, we're going to look at Desmos. Alright, so what I've done here is I've input our function into Desmos, and I had to set the restriction for x is greater than or equal to 0, because remember that x is time, and it doesn't make any sense to talk about what happened before this infection started. So our time starts at 0. Notice that there is no graph here, and that's because our values at the beginning were pretty large, right? Remember, when n is 0, there were 167 people infected. So we're going to have to actually zoom in a lot. So I'm pinching and zooming, And I'm scrolling over here. There we go. To where you can see the red graph. Can you see that? Starting at about 167. And then if I continue to zoom in, whoa, look at that. That's crazy. I don't know if you can see that or not, but this red graph at 0, it's 167, and then it goes almost straight up. It looks like it's straight up, but it's not. It's almost straight up. That means the infection was severe. People were infected like crazy at the beginning. But then, up here at the top, if we zoom in, you're going to see that after, let's see about where that is. Yeah, okay, so the x-coordinate is the time. So 16, there's 17 days, 18 days, 20, at about 20 days is where we get, well, it's 3,499.5. That would round to 500, but it's not exactly 3,500. It rounds there, but it's not exactly that. And then if we continue to go out, you're going to see that at 32 it says 3,500, but that's only because it rounded it up. So even though Desmos says 3,500, it's not actually 3,500 because it's rounding. Let me see if I can zoom in and show you that. You see, no matter how much I zoom in, it's approaching 3,500. And then if I continue to zoom in, do you see that? It continues to approach, but never get there. In fact, if I go over, it's going to look like it touches, but if I zoom in, it doesn't. So what's the bottom line there? The bottom line is, it says, using this model, can you say whether all 3,500 people will ever be infected? Explain. Maybe your answer is yes, because eventually everybody does have to be infected. But mathematically, the answer is no, because that's a horizontal asymptote, okay? Okay, I'm going to say the correct answer, either yes or no, is going to be based on your explanation. Yes, technically, everybody will probably get infected, right? Mathematically, no. The graph, the value of 3,500 can never be achieved because that's a horizontal asymptote. Alright, that's going to do it for this particular lesson. If you have any questions or comments about anything that I've covered, please feel free to leave those in the comment section below, or you can text me, and thanks for watching.